So the next talk is EnclaveFuzz, I believe. Yeah. I believe all of the authors cannot be here, and you are the replacement for the talk, right?
Yeah.
So maybe you can just help introduce your name and start the talk.
Sure.
Thanks.
So hello everyone, I'm Zhou Ming from Tsinghua University, and happy to be here to share our paper EnclaveFuzz with all of you. And we'll first introduce some background. So Intel SGX is actually a set of security-related instructions that are built into some Intel CPUs, and which allows application to create like secure enclaves. And enclave will be loaded into a protected memory region during its execution, and can be used to protect both sensitive data and code. And so next, I will elaborate some details about SGX applications. So at its core, an SGX application has two main components: a host application and enclave. As it is, and to build an SGX application, developers must write code for both parts. And for the host application, it usually contains code to launch the enclave, and it usually contains code to launch the enclave when you start up the application. And for the and also, since the enclave itself cannot directly talk to the operating system, so it's up to the developer to come up with some workaround for that communication. So the host application also contains some code to help the enclave to interact with the OS. And for the enclave, here is like a secure vault where all the sensitive data will get processed. And to make those code and to make both part of the code into an SGX application, Intel SGX SDK will generate some bridge code, like here. Will generate some bridge code and also pack some runtime routines into both part of the host application and the enclave itself. And the right picture shows the memory layout of a loaded enclave during its execution. And when an enclave is loaded into memory, and everything within the enclave is protected by the CPU, and could remain secure even the host application is compromised. And from the view of the memory layout, we could see that the whole enclave is mapped from a special memory region. It's called the EPC memory, and everything within the EPC memory is only accessible to the CPU itself. And the enclave data and the enclave code is under the protection from the hardware. And since the tech model of SGX assumes that everything except the CPU itself could be malicious, including the operating system, peripherals, and etc., such assumption makes SGX attractive for users seeking top-level security. And despite SGX's robust attack model, it is not completely invulnerable. And the code running within enclaves is still prone to some commonly memory corruption vulnerabilities. And such problems have already gained attention from academic community. And like TERX and CoinAttack, two work apply symbolic execution to find potential memory-related bugs, but they may fail to test the large-scale application due to the limitation from like state exploration and unsolved constraints. And SGXFuzz utilizes page fault feedback to recover input structures from enclave binaries and may fail on some complex inputs. And besides, SGXFuzz can only detect limited types of vulnerability due to the lack of the sun tether. And FuzzSGX is another concurrent work. I know the name may be a little misleading, but I'm sure it's actually another work. And it uses program mutation to generate various host applications to test the enclaves, and it shares the same limitation to detect more types of bugs. So in summary, current fuzzing solutions to test enclaves have several limitations. First, current solutions have insufficient understanding of the input structures and dimensions. Since the enclave shares the same virtual address space with the host application, the enclave can directly access data located in the host application, which also forms a new input dimension of enclave. And second, current bug oracle like ASAN is incompatible with SGX applications and cannot detect SGX-specific vulnerabilities. Third, as before mentioned, the Intel SDK will pack some runtime routines into the enclave, which is not our target on the test. Such redundant routines may hurt the efficiency of fuzzing. And to tackle this problem, to tackle those limitations, we propose a new fuzzing framework for SGX enclaves, which has 3 key components. The first is a harness generator, as it shows here. It would take the enclave definition as an input and generate test harnesses to interact with the enclave in 3 dimensions. And we also have an optimized SDK, which will pack the enclave code from developers as a virtual enclave to speed up fuzzing. And next, we have a sanitizer designed for SGX applications to detect more types of bugs. So next, I will elaborate the design of each part. So first, here is an example to show how Intel SGX SDK will pack the data come into or come out of the enclave by generating bridge code. And the code snippet in the left demonstrates C-style functions with some customized annotation on the parameter. And the SDK will generate a pair of bridge code, one for the host application and another for the enclave. And the bridge code will the bridge code that will be packed into the enclave is called trusted bridge, and shown in the right. And the trusted bridge contains sanity checks to verify the size of pointers. Like we have some set check here. And if an input fails to pass this sanity check within the bridge, the execution will be terminated immediately and never reach the developer's code. And to overcome such problem, EnclaveFuzz analyzes the enclave definition field to generate harness that can allocate data with proper size during fuzzing. And it has also mentioned that the size of an argument can be decided dynamically by another argument, like the figure shows here. The size of argument 2 is determined by the value of argument 3, and our harness needs to allocate the proper values for both arguments during test. And then EnclaveFuzz analyzes attributes of the interfaces defined in the definition field to locate pointers that will be copied into the enclave and try to allocate data with correct size for these pointers during the fuzzing. And next, as we mentioned before, the enclave shares the same virtual address space with the host application. So if a pointer points to the memory outside the enclave is dereferenced during execution, it also arises security issues. So in summary, our harness provides data to the enclave under test through 3 dimensions. And the input that is the input parameters of equal functions, and also the return value of the equal functions, and also some untrusted memory access. And also in addition, we extend the untrusted memory access to test the potential time of check and time of use bug. And so EnclaveFuzz will collect all load instructions and utilize diffuse chain to determine if a load instruction could be used by a subsequent compare instruction. And if so, those load instructions are marked. And further, we'll perform runtime check and perform mutation of the value of the the load instruction during runtime to test potential bugs. So next, let's move to another component, the optimized SDK. So EnclaveFuzz packs enclave code under test as a standard shared library. Such design helps further get rid of redundant memory management and context switching routines. So in summary, the optimized SDK tries to eliminate redundant routines introduced from the Intel's SDK, as shown in the dash box here. And to speed up the fuzzing, and the sanity checks within the trust code are kept to ensure our bugs, to ensure the bugs found are not false positives. And our evaluation shows that all bugs found in our virtual enclave execution environment are reproducible in a real hardware enclave. And to detect common memory corruption bugs, we follow a similar design as ASIGN, which uses a shadow map to detect out-of-bound and dangling pointer dereferences, and a God page to detect non-pointer dereference. And also, since the virtual enclave will be loaded in as a standard shared library by the fuzzer, the fuzzer and the virtual enclave share the same heap and stack memory to identify if a memory region is trusted by the enclave or not. During fuzzing, we implemented the shadow bat using ASIGN to mark if the memory is accessible or not. And to detect time of check, time of use bugs, we follow a two-stage analysis. First, we will perform compile time analysis. EnclaveFuzz will collect all load instructions and utilize diffuse chain to determine if a load instruction could be used by a subsequent compare instruction. And second, during the runtime, EnclaveFuzz will hook all load instructions and maintain a query to record the memory address visited by loads for comparison. And if other load instructions are executed, the EnclaveFuzz will check for any overlapping between the visited address and those record and with addresses recorded in the query. And any overlaps are considered as a potential time of check, time of use vulnerability, and like the address C here shows. So next, let's briefly go through the implementation of EnclaveFuzz. So during the pre-processed stage, we analyze ADL field, that is enclave definition field using scripts. And we also developed several LLVM error passes to analyze the enclave source code. And the harness generator is also an error pass to generate a harness can bridge the fuzzer data and the enclave under test. Next, let's move to the evaluation. First, we evaluate EnclaveFuzz to see if it can find new bugs. And totally, EnclaveFuzz found 160 bugs in around 20 real-world open-source enclaves. And among all bugs, most are non-pointer dereference and time of check, time of use bug. And most developers are not that familiar with the security assumption of SGX, and they may not they may not check pointers, just use it within the enclave. And second, we conduct experiment to see if EnclaveFuzz can generate more valid inputs to pass the sanity checks and explore more unique code from compare with existing tool. And the result shows that EnclaveFuzz covers more code coverage and generates more valid inputs compared with SGXFuzz. And next, we perform an application study to verify if the optimized SDK increases the speed of fuzzing enclaves. And the result shows that the fuzzing optimized SDK is around 6.9 times faster than the hardware mode SDK. And we also conduct some application study to show if the multi-dimension inputs contributes to trigger more bugs and the overhead of sanitizers. Please see the paper for more details. And Thus, we will open source our implementation and to help the SGX community, and thanks for listening.
Okay, since none of the author cannot be here at NDSS, if you have questions, please just send emails to the authors with your questions. Okay, let's thank the speaker one more time.